Okay, so in the last lecture, we spent the majority of the time discussing different properties of solutions to Laplace's equation in both 2 and 3 dimensions. And in particular, we looked at different invariances of this Laplacian operator under rotations in both 2 and 3 dimensions. And then we also discussed how you can rewrite the Laplacian in terms of polar coordinates in 2 dimensions and in terms of spherical coordinates in 3 dimensions. And we saw how you can use this perspective to, with additional assumptions, solve Laplace's equation. In particular, if your solution U has some kind of rotational symmetry, meaning the value of the function doesn't change if you rotate your coordinates, we were able to solve the equation in both 2 and 3 dimensions by using the representation in terms of polar coordinates and spherical coordinates, respectively. Right. And so what we're going to do today is continue along this theme of actually trying to solve the equation, right? We have a variety of properties that must hold for solutions to Laplace's equation, but we don't currently really know, except in the few examples we saw last time, we don't really know how to solve the equation. And so what we're going to focus on today is solving the equation in 2 dimensions on a very specific class of domains. And in particular, we're going to focus on solving Laplacian U is equal to 0, which is the Laplace's equation on rectangles in 2 dimensions with given boundary conditions. Right, so more succinctly, we're going to today study the boundary value problem for Laplace's equation on rectangles in 2 dimensions. Right, and so in the corresponding chapter in the book, there's also a separate section which is devoted to an analog of what we're going to look at for 3 dimensions. So instead of rectangles in the plane, for example, you could have a 3-dimensional rectangle or a cube or something like that. So, I mean, unfortunately, like adding an extra dimension kind of increases the technical difficulty of solving this problem without really giving you any new insight into the problem. So for this class, we're going to be focusing on the 2-dimensional case. So in homework problems and on exams, I'm only going to require you from this section in the book, which is, I guess I should specify 6.2. I'm only going to require you to understand the 2-dimensional case because I think it covers the major points of what you should know from this section. Right, and I do want to point out that everything we're going to be talking about, unfortunately, only works if your domain is a rectangle. So it turns out that if you change the domain where you're trying to solve Laplace's equation, the methods that you have to use in order to solve it can change dramatically. And so it turns out that for us, given the toolkit that we've developed so far, rectangles are the easiest domain to look at for solving Laplace's equation, which is why we're starting here. But unfortunately, this is only the beginning and not the end of the story. Right, and so maybe diving into more of the specifics, what are we actually going to look at today? So we're going to study the following boundary value problem. Right, and so let's say, right, we're looking in 2 dimensions. So let's say this is the XY plane. Well, we're going to look at Laplace's equation in a domain D, where D is given by a rectangle. And so to simplify some of the calculations, we may as well assume that our rectangle is based at the origin. So maybe it looks something like this. Right, and so we'll assume that that this rectangle is our domain D and that the left endpoint of the rectangle is based at the origin. We don't need to assume that the left endpoint of the rectangle is based at the origin because remember from last lecture, we saw that the Laplacian is invariant under translations. And so if your domain D is a rectangle which does not have its lower left corner based at the origin, you can always shift your coordinates to move it to the origin. then solve the problem as we're going to solve it today. And then once you have a solution, you can shift your coordinates back to the original domain using translation invariance. Right, so it suffices to look at this case. And so this will be our domain D. And so we can describe this by two inequalities, right? So let's say x is between 0 and A, and y is between 0 and B. Well, then the domain is described by, well, just by writing down both these intervals, right? Right, so x is between 0 and A, and y is between 0 and B. Okay. And well, we're going to, in order to actually get a solution, we're going to have to prescribe certain boundary conditions, right? And so in order to understand the boundary conditions, we first need to understand what the boundary of this domain is, right? Well, the boundary is just going to be what I'm drawing in blue now, these 4 lines, right? And so I'll write this as boundary of D. And so we can describe this by 4 separate equations, right? So since we have like corner points, you have to like use separate equations for each piece, right? So, but this should otherwise just be a familiar small little exercise. So, right, so let's just write down the equations of each of the 4 boundary lines, right? So the first one, well, on the bottom line, we have y is equal to 0. We also have the top line, which is when y is equal to b, right? Well, we also have the left and right lines. So these are when x is equal to 0 and x is equal to a, respectively, right? And so we also have x is equal to a or x is equal to b, or sorry, x is equal to, excuse me, x is equal to 0 or x is equal to a. Right, and these describe the 4 boundary lines, right? And so we're going to look for a function u such that the Laplacian of u is equal to 0 inside the domain with certain prescribed boundary conditions on the boundary, right? So maybe on the top boundary, u is equal to some function g, right? So this is like a Dirichlet condition. Maybe on the right part, I'm assuming something about the derivative. Maybe the first derivative is equal to h. Maybe on the bottom, we assume u is equal to some other function f. And maybe on the right, we have some mixed condition. For example, this condition, which we haven't talked too much about in the lectures, although it has shown up in at least one homework problem, is the Robin condition, where maybe I have some information about the sum of u and its derivative. Maybe uy plus u is equal to some function p. Okay. Right, so we'll specify certain boundary conditions. And these will be assumed to be functions that are given to you. And so what we're going to do is, given certain boundary conditions, and assuming that u solves Laplace's equation in the interior of the rectangle, we're going to find a solution that satisfies all of these properties, right? So we'll find a function, given these functions on the boundary, we'll find a function that is harmonic in the interior of the rectangle, and for which also solves all these boundary conditions, right? And so just as we've seen with several of the other problems we've looked at, you really need to specify certain boundary conditions in order to solve the problem. If you don't indicate the behavior of your function u on the boundary, you're not going to be able to completely solve the Laplace's equation, because there could be many different solutions depending on what the boundary conditions are. However, as we saw last time, since we have a maximum principle, once you specify the boundary conditions, they will uniquely determine the solution, right? Okay, and so we'll spend most of the lecture just looking at one particular example in detail. So let's move on to this example. Right, and so in this case, we're going to continue with the rectangle from before. So let me just copy over our domain. Right, so the domain D is the interior of the rectangle, and the boundary is the collection of blue lines. Maybe up here, to be more precise, I should have put strictly less than in the inequalities, right? So, right, and then once you add in the equals correspond to the boundary points, right? So maybe this is a little bit more precise. And so we're going to look at the boundary value problem with mixed boundary conditions, meaning different lines on the boundary will have different types of boundary conditions. In a lot of applications, maybe all the boundary conditions will be of the same type. For example, you may have only Dirichlet boundary conditions, but there are also examples where maybe you're interested in more complicated boundary conditions like this. And so it helps to look at, it's instructive to look at an example where you have to deal with different types of these conditions at once. Great. And so in particular, we're going to assume that, well, on the top, let's assume that on the top boundary line, we have a certain Dirichlet condition where u is equal to some function g of x, right? Let's assume on the left-hand boundary line, we have u is equal to 0. Let's assume on the right-hand side, we have not u equals 0, but the derivative of u is equal to 0. And let's assume on the bottom line, we have a more complicated condition. For example, maybe derivative with respect to y plus u is equal to 0. Right, so the top condition is called a Dirichlet condition. This is also a Dirichlet condition, right? Because we're just specifying, whenever you specify values of just the function u on the boundary, that's a Dirichlet condition. When you specify values of the derivative, this is a Neumann condition. And in particular, notice that this is the x derivative, which points in this direction. So when we define the Neumann condition last time for Laplace's equation, it involved like derivative in the normal direction. But at these points, x is the normal direction, right? So this is like the flux of u in direction x through this boundary. And this final condition on the bottom, which is more complicated, is called the Robin condition. Right. And so more precisely, what are our boundary conditions? So we're assuming, let me write them out. We're assuming that the first one was the Dirichlet condition. So when y is equal to b, I want to specify u of xb is equal to g of x. When y is equal to 0, I'm going to specify, when y is equal to 0, we have this Robin condition. So this says that uy of x0 plus u of x0 has to equal 0. And then we have the two conditions corresponding to when x is 0 and x is a. So when x is 0, we want u of 0y to be equal to 0. Right, so that's this condition over here. And then finally, we have the Neumann condition, which says that the x partial derivative at 0 comma y should be equal to 0. Right. And so these taken together are the conditions for our boundary value problem, right? And so g is just some function that's specified, maybe like sine x or e to the x times sine x or something like that, right? G is just some given function. And what we want to do is find a function u such that inside the domain, the Laplacian of u is equal to 0, and such that all of these boundary conditions are satisfied. Right? Okay, well, let's look at the PDE we're trying to solve, right? So Laplacian of u is given by uxx plus uyy. So notice that there's no mixed partials. So we expect, as we've seen in lots of examples, if there are no mixed partial derivatives, we should be able to get somewhere using separation of variables. Right, and so this is what we're going to do. Right, so let's begin by, so this will follow this process which we saw many times before. for the boundary value problems for the diffusion equation and the wave equation, it's going to be a similar process, but some minor things will change since the Laplace's equation is a little bit different, and two, the boundary conditions are a little bit more complicated in this example. So what we'll begin with is, well, let's just guess, right? We want to try separation of variables. So let's guess a solution of the form uxy is some function of x times some function of y, right? So let's say u is f times g. Maybe to avoid confusion, let me change the g over here to an h, right? So instead of u, the Dirichlet condition is u is equal to h of x when y is equal to b, right? Okay, and so what happens if I have a solution of this form? What happens if I apply the Laplacian, right? So this tells me then that Laplacian of u is equal to, well, second derivative with respect to x plus second derivative with respect to y of f of x times g of y, right? But the x operator here is only going to act on f, and the y operator here is only going to act on g, right? And so if you write this out, you end up with, well, this is equal to f prime prime, right? You take two derivatives of x. This is from the x operator, and it doesn't do anything to g. And then you also add on the piece corresponding to second derivative with respect to y of this product. So you get f of x times g prime prime of y, right? And again, the reason that separation of variables is so useful here, and the reason why we're trying it, is exactly because I have the partial derivative operators here involve separate variables, so there's no mixed derivatives, right? If you have mixed derivatives, separation of variables may not be a very good technique, but here it will turn out to be a good technique. Right, and so what we want to do is solve this being equal to 0, right? I want Laplacian of u is equal to 0, right? So I want to solve 0 is equal to f prime prime of x times g of y plus f of x times g prime prime of y. Okay, so we know what to do at this point. What we're going to do is try to separate the variables and bring everything in depending on x on the left-hand side and everything depending on g on the right-hand side. Well, this tells me then if I try to do that I need to have f prime prime of x divided by f of x should be equal to the negative of g prime prime divided by g, right? Well, since the left-hand side depends on x and the right-hand side only depends on y, and these are two separate variables, this can only happen if they're both equal to some constant, say alpha, right? And so if I rearrange, or if I use this observation, well, this tells us that, well, we need f prime prime of x has to equal whatever this constant alpha is times f of x, and also g prime prime of y has to equal the negative of alpha times g of y, right? And so these are the two ordinary differential equations that we now have to solve simultaneously in order to get a solution to Laplace's equation in this special case where we have some function of f of x times some function of y. Okay, well, we remember, or we've seen how to do this in a variety of examples related to the diffusion and the wave equation. So remember, let's assume that alpha is a negative real number. So let's say alpha is minus beta squared, where beta is a real number, right? And so in this case, we saw that we can solve for f in the following way. Well, f has to equal, or the general solution is given by f of x is some number a times cosine of beta x plus some number b times sine of beta x, right? And so this is a good candidate for our function f. Unfortunately, once we pick alpha to be negative, right? Well, we know how to solve for f, right? Over here, though, if alpha is negative, then that means that negative alpha is positive, right? So over here, we need minus alpha has to be positive. And so therefore, we're not going to be able to solve this ordinary differential equation using sines and cosines in this way, right? This formula only works if this constant coefficient, when written in this way, is negative. But here, if it's negative, this is going to be positive. So once we fix this as our choice for f, we're going to have to use a slightly different method to solve this ordinary differential equation, right? So we're not going to get sines and cosines is the point. But nevertheless, we can still solve it using the same methods that would lead you to this equation. And so in particular, what I'm going to do, you may remember this from from either calculus or ordinary differential equation class. In order to solve for g, I'm going to guess maybe g is equal to some number. Let's just say the coefficient is 1, but let's say g is equal to actually, no, let's leave it with a constant. So some number c times e to the ry, right? So we're going to guess some kind of exponential solution with r a real number, right? Okay, well, let's plug in this guess into our equation. Our equation says g prime prime of y plus alpha times g of y is equal to 0. If I plug in this definition for g, I end up with r squared times c e to the ry, this is g prime prime, plus alpha times c e to the ry, that's alpha times g, is equal to 0. And so this tells me that I need r squared plus alpha. Right, since this is an exponential, exponentials are always non-zero, so I can now cancel out these exponential terms, and I get r squared plus alpha has to equal 0. This requires that r squared is minus alpha, but minus alpha is beta squared, right? And so this is consistent, right? Because beta squared is positive and r squared is positive, so I can always solve this, right? And so in particular, this tells me that r is plus or minus beta works, right? And so in particular, I can take either c times e to the beta y or c times e to the minus beta y, and both of those will give me solutions. Since this equation is linear, I may as well add those two together to get a more general solution, right? So we're going to use the linearity and add them together to get to combine these two. And so then we're going to end up with our function g, well, maybe some constant c1 times e to the beta y, plus potentially a different constant c2 times e to the minus beta y. And so that's going to be our candidate for g. And so going back here, well, now we know we have a good candidate for f, and we have a good candidate for g. And so the next step, following what we've done before with these problems, would be to try to determine some information about what these constants have to be and also what beta has to be by using these boundary conditions that we've been given. Right, so once you do the initial step of solving these ordinary differential equations, the next step is to try to start using the boundary conditions to simplify your solution into a more tractable form. It turns out that for these types of problems, when we're dealing with exponentials, it helps for computation to rewrite this formula for g in a slightly different way. And so what I'm going to do is just do a little bit of a digression to get to that point, and then we'll return to solving the problem. Right, and so as a digression, it's helpful to write this function g in terms of what are called the hyperbolic sine and cosine functions. Right, so in particular, let me remind everyone what the definition of hyperbolic sine and cosine are. So the hyperbolic sine, which is denoted sine with an H, I think sometimes it's pronounced sinh. Right, so hyperbolic sine of y is given by e to the y minus e to the minus y over 2. And the hyperbolic cosine, which is sometimes pronounced cosh of y, is given by e to the y plus e to the minus y over 2. And so these formulas should look formally kind of familiar to you if you think back to our complex definition using complex exponentials of sine and cosine. These are kind of like the analogs if you don't have complex numbers here. So these are just real numbers y. And so these are the definitions of hyperbolic sine and hyperbolic cosine. And so you can check that if you take the derivative with respect to y of hyperbolic sine, that this is hyperbolic cosine. Right? So it behaves kind of like a trig function because you differentiate sine and you get cosine. And also, if you take the derivative of hyperbolic cosine, it doesn't give you minus hyperbolic sine, it just gives you hyperbolic sine. Right, and that's just this is just going to follow from the chain rule and the fact that, right, if you differentiate e to the y, it doesn't change. If you differentiate e to the minus y, it will just change the sign out here, right? And so when you take derivatives, you flip back and forth between these two. Right. And so also, we'll notice that I can convert between exponentials and these hyperbolic sine functions pretty easily. For example, so here's another fact which we're going to use above. So notice that you can write e to the y as hyperbolic sine plus hyperbolic cosine, right? Because the two negative terms will cancel, or the e to the minus sign has different, e to the minus y has plus or minus signs, and so those will cancel when you add them. And then you'll have e to the y over 2 plus e to the y over 2, which just gives you e to the y. And similarly, e to the minus y can be given by hyperbolic cosine minus hyperbolic sine. Okay. And so if we come back to this formula for g, well, what I'm going to do is I can replace e to the beta y by some combination of hyperbolic sine of beta y and hyperbolic cosine of beta y. And similarly for e to the minus beta y. And so let me say that these constants are C1 tilde and C2 tilde. What I'm going to do is plug in these formulas for e to the y and e to the minus y respectively, and I'm going to write my solution in terms of hyperbolic sine and hyperbolic cosine, right? Right, and so we can write g of y as some number C1 times hyperbolic sine of beta y plus some number C2 times hyperbolic cosine of beta y for certain constants, which are, well, C1 and C2 may be different than the C1 and C2 that I wrote here, which is why I put the tilde here. But since they're arbitrary constants and we don't know what they are, let me just rewrite them as C1 and C2 again. Right. Right, and so now our initial candidate, or our initial guess, well, we have u of xy is given by f times g. Our function f was a times sine of beta y, or sorry, x, plus b times cosine of beta x, and then multiplied by this new term involving the hyperbolic functions. So sine h of beta y plus c2 cosh beta y. Right, and so this is our initial candidate. And so now what do we want to do? Well, we want to use the boundary conditions. To simplify, or to figure out what the constants are. Right, so we want to, the most important thing right now is to figure out what should beta be, right? And then after we find out, hopefully along the way, we'll also be able to simplify some of these constants. Like maybe, for example, some of them are actually 0, right? So we have to use the boundary conditions to do this. Let me just come up here and copy over the boundary conditions. Okay, so I'll just copy these back down over here. Right, so these were our boundary conditions. Okay, and so at this point, you have to kind of work strategically. So you don't really know which one to start out with. Generally speaking, whenever you have zeros, zeros will simplify things. So we may want to start by looking at one of these conditions involving the zeros. So on your like list of decisions, you should first look for conditions that involve like something being equal to 0. Next, well, derivatives are usually a little bit more complicated than no derivatives. So let's actually first look at this condition: u of 0, y is equal to 0. Right, so if I use this condition, what does this tell us? Right, so we have 0 is equal to u of x u of 0 comma y. Well, what happens if I plug in x equals 0 into this above equation? This tells me that 0 has to equal, right? So I'm going to let me plug in x equals 0 here. This is going to tell me I need 0 is equal to b times cosine of, well, cosine of 0, it doesn't matter what beta is, cosine of 0 is 1, so I just get b. And then I have c1 times hyperbolic sine of 0 plus c2 times hyperbolic cosine of 0, right? Well, notice that if I come back up here to the definitions, well, what is the hyperbolic sine of 0? Well, this is e to the 0 minus e to the 0 over 2, which is 0, right? Hyperbolic cosine of 0 is e to the 0 plus e to the 0 over 2. Well, e to the 0 is 1, so this is 1 plus 1 over 2, which is 1. Right, so this is 0 and this is 1. And so if I plug this in, I get 0 is equal to b times c2, right? And so that means that either b or c2 is 0, right? So we can pick one of these to be 0, right? So either b or c2 is 0, right? It doesn't mean that they're both 0. One could be 0 and one may not be, or they could both be 0. We don't want to make both 0 because maybe we're losing too much information if we let both be 0. So let's, for example, set b equals 0. This is kind of like an arbitrary choice, and maybe you would have to, if you got to a point where you couldn't solve, you would come back to this step and instead try b non-zero and c2 equals 0. But let's for our purposes say that b is equal to 0, right? And so that means that the cosine term here drops out, and so we end up with now u is given by a times sine of beta y, or by beta x, excuse me, times c1 hyperbolic sine of beta y plus c2 hyperbolic cosine of beta y. Right, and so this is our slightly simplified solution, and now we've used the first boundary condition corresponding to when x is equal to 0 on the bottom of the rectangle. Right, so the next thing we're going to do now is move up to, right, so this Robin condition still looks a little intimidating, so let's just move up to this Neumann condition, which just involves the first partial derivative. Right, and so, right, so I just noticed there's a typo here in the Neumann condition. So remember, this was not x equals 0, but x equals a. So let me just go and fix this quickly up so it's consistent in the notes, right? So this should have been an a, right? Because remember, we're looking at at this condition over here. And so we know that the first derivative with respect to x is 0 when x is equal to a, right? Okay, and so now what we're going to do is use this Neumann condition on the right boundary line of the rectangle to simplify our solution further. So let's use the condition, the boundary condition, ux of ay is equal to 0. So what we want to do is first calculate, well, what should the derivative of u with respect to x be, using just the formula that we've obtained up here. So if I calculate ux at x comma y, this gives me, well, of course, the x derivative is not going to land on any of these terms because they're all constant with respect to x. So I just have to differentiate the first term here. And so I end up with a times beta cosine of beta x, and then times the remaining terms, c1 hyperbolic sine of beta y plus c2 hyperbolic cosine of beta y. And now what I'm going to do is set x equals a. Right, and so when I set x equals a, well, then I have 0 is equal to ux at a comma y, which is equal to a times beta cosine of beta a times the remaining terms. Right, which don't change since since we're not doing anything to y. Right, well, now I can certainly choose y so that this term here involving the y component of the solution is non-zero. And well, I can assume that this constant a here is also non-zero, or else my solution is just the trivial solution, and I can assume beta similarly for beta. And so if I divide by the terms that I've underlined in blue, this tells me that I need to have 0 equal to cosine of beta a, right? And so this tells me that whatever beta is, beta times a is a 0 for cosine, right? But we know what the zeros of cosine are. Remember, the zeros of cosine are given by odd multiples of pi, right? So this is an odd multiple, oh, sorry, of pi over 2, excuse me, of pi over 2, right? And so, well, one way to write this is that, well, therefore, you can write this as beta a is equal to some integer n plus 1/2 times pi for some integer n bigger than or equal to 0, right? Because I can replace n by 2n over 2, and then I have 2n plus 1 over 2, which is an odd number over 2 times pi, which is exactly what we just said. And so, well, then this tells me that I know what beta is in terms of a, right? Beta is given by n plus 1/2 pi over a for some integer n bigger than 0. And so what I'm going to do is, well, since this works for each such integer, let me just index beta by the integers and define beta n to be this quantity, right? And so this works for each integer, right? And so now going back to our candidate for a solution, well, now we've simplified it further in the sense that we know what beta should be, right? So for each integer n bigger than or equal to 0, we get the following candidate for a solution. Well, u should be some number a times sine of beta n x, and then times the hyperbolic trig terms, right? So I get c1 hyperbolic sine of beta ny plus c2 times hyperbolic cosine of beta ny, right? And so this is what the Neumann condition ultimately told us. It ultimately allowed us to determine what beta is equal to, right? And so now we've used this Neumann condition here. And now we have 2 more, we're not done yet, of course. We have 2 more boundary conditions to work with. But we at least know that, right, we at least have like a basic skeleton for what the solution should be. And going off of what we've seen many times before, of course, we're ultimately going to end up summing over all n, right? Since since this formula here gives us a solution for each integer n, and since the Laplace equation is linear, we can get a more general solution by summing up these terms from 0 to infinity, which we're ultimately going to do. However, it's going to turn out that it's a little bit easier if we first, before doing that, we first try to see what information we can gain from this more complicated Robin condition, right? So the reason why you may think, okay, before summing over n, let's first examine this Robin condition is that, well, the other condition here involves a general function h, right? And so understanding how the solution will look in terms of a general function h is going to be a little bit harder because we don't know anything about h. At least in this condition, we just have the solution u and its derivative at a certain point set equal to 0, right? And so we're not going to have to use more extra outside information about this, right? And so what we're going to do next is first, before trying to sum over n, let's see what this Robin condition tells us, right? So next, we're going to use the condition the Robin condition, which is u of, excuse me, let me remind myself. Right, when y is equal to 0, right? So uy of x0 plus u of x0 is equal to 0, right? So this was the boundary condition on the bottom of the rectangle when y is equal to 0, right? And so what we want to do is just calculate, let's just calculate these two terms, right? So I have uy of xy, right? Remember, you need to calculate it as a function of y and then plug in y equals 0, right? Otherwise, it's not going to match up, right? So let's take the derivative of our candidate for a solution, which is right here with respect to y. Well, we end up with a times sine of beta and x. And now we're going to have to remember our derivative formulas for hyperbolic sine and cosine. Remember, when you take derivative of hyperbolic sine, you get hyperbolic cosine, right? So I get this, right? But now I have to use the chain rule, so there's an extra beta n that shows up. And also, well, when I differentiate the second term, I'm going to get C2 now hyperbolic sine beta n y, and then I also have to multiply by beta n again because of the chain rule, right? And therefore, if I plug in y equals 0 to this derivative, I end up with a sine beta n x times, well, now remember that if y equals 0, I get, right, hyperbolic cosine of 0 is 1, and hyperbolic sine of 0 is 0. Right, so if I plug these in, I end up with C1 beta n, and that's it. Right. Now, what is the, right, so this is, I've evaluated the first term here. I also want to look at u of x comma 0, and then I need to plug them into this equation, right? Right, so we also have u of x0. Well, this is a little bit easier. We just end up with a times sine of beta n x. We're plugging in y equals 0, so we're only left with, well, the sine, now we're plugging in for 0 here. So the C1 sine h term vanishes, right? So I get 0 plus C2 hyperbolic cosine of 0, which is just 1, right? So I just get C2. Right, so this ends up being a times C2 sine of beta n x, right? And so now if we plug these into our boundary condition, what do we end up with? Well, I know that uy of x0, which is a sine beta n x times C1 beta n, it has to be the negative of this term, right? So this is equal to negative a times sine of beta n x times C2, right? And so now let me cancel the like terms, which I can do because, well, just choose x so that this is non-zero, and then you can divide. And so then you end up with, well, this tells me that C1 beta n has to equal minus C2, right? Okay, and so now we're at a point where you may pause for a minute and think, like, how do we proceed from here? But you should think back and remember that we're just trying to find a particular solution, right? We want to make things as easy for ourselves as possible in order to ultimately get to a solution. Right, at every step of the way, we're using a different boundary condition to simplify matters a little bit further and kind of guide us along. But there are certain points where we're allowed to make a choice with that, as long as it doesn't conflict with anything we've done up until this point. And so here this says that there has to be some relation between these constants C1 and C2, and also among themselves, and also with respect to this beta n parameter. Let's try to just make this relation as simple as possible. And so in particular, why don't we just take C1 to be 1, right? And if C1 is 1, well, then we would want to take C2 as negative beta n, right? We're just choosing the simplest choices that we can make in order for this equation to hold. And okay, well, let's now plug these in, right? So then we get for each integer n bigger than or equal to 0, we end up with our function u of xy is given by some constant a. Now let me index the constant a to also depend on n, because it ultimately will. So I have an sine of beta n x. And well, now I know what C1 and C2 are. So I have now the hyperbolic sine of beta n y, now minus beta n hyperbolic cosine of beta n y. Right, whereas before beta n is given by n plus 1/2 over a times pi. Right, and so now we've successfully used the more complicated Robin boundary condition to simplify the solution a little bit further, right? So let's go back to our list of boundary conditions. We've used this one. So finally, it remains to just understand how to use this condition to finalize our solution, right? And so here we have an arbitrary function h of x. And so ultimately what we're going to do is write down a particular version of a Fourier series and then use Fourier coefficients of h to get a solution, as we saw in some earlier examples. Right, and so what the first step that we want to take now is get a more general solution by using linearity. Right, so using linearity, let me change, sorry. We arrive at a more general solution which is given by u of xy is the sum from n equals 0 to infinity of an, I have sine beta n x, and then times all my hyperbolic functions, hyperbolic trig functions. Right. Where beta n is defined as above, right? And so now what I'm going to do for the purposes of, for sort of clarifying some things, well, let me simplify the expression here to only involve terms involving x, right? So you can imagine that if I combine the terms that I've just underlined in blue, well, sorry. Remember that y can be treated as a constant as a function of x, right? If you fix y and view this as a function of x, well, then I just have some coefficients times sine of beta n x. And so this looks a lot like a sine Fourier series. And so it's not quite a sine Fourier series, but it's going to essentially reduce to that type of problem. Right, and so let's proceed with this idea. And so, well, remember from the boundary condition, if we set y equals b, we have h of x has to equal u of x comma b. Remember, this is the boundary condition at the top of the rectangle. And so this is equal to the sum from n equals 0 to infinity. Let me combine the two terms that are underlined in blue. So let me just write cn for those. And then I get sine of n plus 1/2 divided by a times pi x, right? where Cn is given by an times the remaining terms, times hyperbolic sine beta n, b, minus beta n hyperbolic cosine of beta nb. Right. Okay, well, the function h here has been, we're assuming it's been given to us from the start, right? So maybe h is like x squared or some step function or something like that, or maybe sine of, or e to the sine of x or something complicated. I don't know what the function is, but it's some arbitrary function on the domain that's been given to us. And we want to write it as an infinite sum of these different sine terms. And so this is exactly a Fourier series. One way to think about this in terms of the original eigenfunction perspective that we looked at, well, these different sine functions here as you vary n, these are the eigenfunctions. Remember, if we had the different x endpoints when x is equal to 0 and as x is equal to a, and we had a 0 Dirichlet condition here, and we had a Neumann 0 condition here. And so if you go back to the lectures from a few weeks ago when we were looking at this from the eigenfunction perspective for the operator minus second derivative with respect to x, these functions here turn out to be the eigenfunctions of this operator with these specified boundary conditions, right? Remember, the boundary conditions were important for determining what the eigenfunctions were. And so that's one way to think about this as a Fourier series. Another way to think about this, though, is just, well, I can rewrite sine as a combination of complex exponentials. And so this legitimately does become, using that perspective, it will become some multiple of a complex Fourier series, and you can calculate the coefficients in terms of h in that way. What I'm going to do to complete this example, though, is maybe combine those two perspectives and remind everyone that, well, since these are the eigenfunctions for this particular problem, you have some kind of orthogonality property. If the eigenfunction perspective is a little too abstract or complicated, you don't have to worry about that because you can just check directly that these functions are orthogonal on the domain x between 0 and a, right? So let me define capital Xn is sine of n plus 1/2 pi over a times x, right? So these things are orthogonal on the interval between 0 and a in the following sense. So if I take the integral between 0 and a of, say, one of these things times another, right? So let's say let's do n and m. Right? This is essentially the inner product of these two functions, right? So I have xn here and xm here. It's the inner product on 0 to a normalized by some constant, multiplied by some constant. Well, this is going to be equal to 0 if n doesn't equal m. And if n equals m, I think it should be equal to, I believe, right, a over 2. Right? Right. And so this is our orthogonality property, which you should check, right? So maybe as a quick exercise, just pause the lecture and do this calculation, or maybe you can just believe me. So it's just going to be an exercise in integration by parts and trig integrals of trig functions, etc. Right? Okay, but assuming you have this orthogonality property, we can calculate the coefficients here just as we would for the usual sine Fourier series. And so in particular, we end up with, well, Cn has to equal, right, so 2 over a times the integral from 0 to a of the function h of x times xn, or times sine of n plus 1/2 pi over ax dx. Right, so these are kind of like the usual Fourier coefficients for this orthogonal system of functions. Right, and so we calculated the Cn here. And so, well, now we're almost done. Well, we want a final formula here in terms of h. In particular, we want to calculate an. Well, what we just did is calculate Cn using the theory of Fourier series, but now Cn is equal to, I know how to write Cn in terms of An, right? I just have to divide by this hyperbolic trig function, right? Right. So since Cn is equal to An times what we had, right, hyperbolic sine of beta and b minus beta and hyperbolic cosine of beta and b. Well, now we know An, right? In particular, An is going to be the Fourier coefficient of h calculated in an appropriate way, in particular with respect to these things, and then divided by this constant, right? And so therefore, finally, we end up with, well, u of xy is the sum from n equals 0 to infinity. I have Cn divided by these hyperbolic trig terms, plugged it with b plugged in. Right, and then times sine of beta and x as before, and then all multiplied by the remaining hyperbolic trig functions. Right? So as you can see, this is certainly not a simple formula. It's in fact a very complicated formula, but that's just the nature of the problem, unfortunately. Right, so this is our final solution formula, where Cn is like the Fourier coefficient of h on the interval between 0 and a with respect to not quite the sine Fourier coefficient, but the Fourier coefficient with respect to sine of n plus 1/2 over a pi x, right? This function. Right, right, and so I do want to point out, as I mentioned a few minutes ago, that if this perspective, like kind of viewing this as a generalized Fourier series for this particular, it's not quite a sine Fourier series because the n is shifted, right? It's an integer over 2. So it's a little bit different than the sine Fourier series we looked at before. If this whole perspective is a little complicated and you don't quite get it, there's another way to look at this, as I said, to find a solution. And this would be perfectly acceptable as an answer if you gave it to me. You can just use whichever perspective you think is easier. Right, remember I can also write this as 1 over 2i times, sorry, let me give myself some more space. Right, so this is 1 over 2i times e to the I n pi over a plus right, n pi over ax plus 1/2 1 over 2a x, right? And then minus e to the minus I times the same thing. And so if you plug this in, well, you'll have maybe some extra term here, which depends on x, which will factor out. But otherwise, you're just going to end up with basically a Fourier series in the complex sense, with coefficients that maybe you'll have to keep track of how they depend on I. But then you can just use our normal formulas for complex Fourier coefficients and calculate the solutions this way, right? So the point is, if this type of formula here is a little confusing because of the shift of the n variable, you can also just go back and use our complex Fourier coefficients, and you'll also be able to calculate the solution this way. So as with a lot of things in math at this level, there's typically a variety of slightly different approaches which will get you to the same endpoint eventually. And so you should choose the approach that you're most comfortable with, as long as it's valid. Right. Okay, and so that's basically the example. And so as you've seen, this has taken us a while to do, and I mean these problems are highly non-trivial, right? There's a lot of steps to keep track of, and we're using a lot of like deep theory, in particular the theory of Fourier series, to actually find a solution in the rectangle. So maybe it would help if I just kind of recap exactly what we did here, right? So this is kind of like the general approach to the boundary value problem, Laplace u equals 0 on a rectangle. Right. And so the first step is always, well, we're going to use separation of variables. Right. And so that's how we began. The second thing to point out is, well, we could have mixed boundary conditions. Right. And so what you want to do is work with the simplest of those conditions to simplify your candidate for a solution, right? Right, for example, we want to, right, what did we do earlier? Well, we looked at first the conditions that had 0 on the right-hand side and which were easier to work with. For example, we began by looking at this simple Dirichlet condition, and then we looked at the Neumann condition, both of which just involve the solution or its derivative at some point equal to 0, which is usually easier to work with computationally. And then we moved up to the slightly more complicated Robin condition, which is a little bit more involved, but it's still not too bad because there's no extra function here, right? It's just things involving the function u. And then finally, at the end, we moved up to this last condition, which involved an arbitrary function h. And this was much more involved because we had to relate this to the Fourier coefficients of h, right? Right, and so, so you're ultimately going to have to use linearity to sum over n. And so this will lead you to some type of Fourier series. And so finally, the fourth step will be to calculate Fourier coefficients. Right, in particular, you'll have some constant coefficients that depend on the integer n, right? For each n, you have a different coefficient. And so the coefficients will depend on the Fourier coefficients for boundary conditions. Right, for the remaining boundary condition, as we did with the function h, right, in the last example. Right, and so this is kind of a skeleton about like that tells you how to approach all of these boundary value problems for Laplacian on rectangles. Each type of problem is going to be very similar, but on the other hand, everything is different slightly because once you change the boundary conditions, your solution will look slightly different, right? So you have to be careful there. Although it is worth pointing out that in step 1, you'll always get, in step 1, like you have a times, remember what do we have? A times sine of beta x plus b times cosine beta x times the hyperbolic trig, right? So say c times hyperbolic sine beta y plus d times hyperbolic cosine of beta y, right? Because to get to this point, this was like our initial candidate before we tried to use the boundary conditions and before we tried to sum over n. Here we just use the Laplace's equation, right? So you can always start at this point, right? You don't have to redo the first step because it's done in the lectures. You can just go back to the lecture notes or the book and check if you forget the formulas, but you can always start here. But then you have to move on to step 2 and start using the specific boundary conditions that are given to you. And if you have different boundary conditions, well, maybe it's going to end up looking a little bit different than we did in this example. So you have to work very carefully. Right? But at least the sort of outline for how to approach this will be the same each time. Okay, and so the next thing I want to do is move on and, right, so this is how to solve the Laplace equation on rectangles in the plane. As I mentioned earlier, there's a similar way to solve the 3-dimensional Laplace's equation in like a 3D rectangle or a cube or something in space with specified boundary conditions. You essentially use the same argument that we did here, except there are more boundaries to keep track of, more boundary conditions to keep track of. And also there's a third variable, right? So when you use separation of variables, you actually end up with 3 different ordinary differential equations instead of 2. So maybe it's a little more complicated to deal with, but in theory, you're essentially doing the same thing with some extra technical difficulties related to the extra variable. And so I don't think that it's much more insightful to focus on the 3D case of the same problem. I think most of the main ideas come across just looking at the 2D case. And so as I said before, we're not going to require you to solve these types of boundary value problems in 3 dimensions, only in 2 dimensions on rectangles. Right? But if you're interested in how this works in 3 dimensions, it's written out in detail in the book. There's an example that's done. Right, and so the next thing that we will move on to, though, is the boundary value problem for Laplace's equation in a different type of domain. And in particular, we're going to look at the Dirichlet boundary value problem for Laplace's equation on disks in the plane. Right, and so what's the big kind of issue with the example we just looked at? Well, here the formulas were incredibly complicated, right? So in general, this is what your formulas will look like on a rectangle. It's kind of surprising that if you change the domain and instead you look at a disk in the plane, it turns out that we actually will be able to come up with a much simpler formula that we can use. And so let's begin with this discussion. So I'll set up the main ideas and do some of the main calculations now, and then in the next lecture we'll finish this. Right, and so here's the problem that we're going to solve. Right, and so let's say we have a disk centered at the origin in the plane. Right, so let me draw a disk here. Say this is the origin. And let's say it has radius A, right? And so let me call this disk dA, which is the disk of radius A, right? And so we can describe this in Cartesian coordinates as the set of all points such that x squared plus y squared is less than a squared, right? Right. This means the distance from the point to the origin is less than a squared. If the distance is equal to a squared, well, then you're on the boundary, right? So this is our boundary. Right, and so the boundary is described by the points where x squared plus y squared is equal to a squared, right? And so what we're going to do is, well, we're going to look for a function u such that Laplacian of u is equal to 0 inside the disk, and on the outside of the disk, u is equal to h, some function h, which is given, right? So we want to find a function u of xy such that Laplacian of u is equal to 0 inside the domain dA, and such that u is equal to a given function h on the boundary. Okay. And so this is what's known as the Dirichlet problem for the disk dA. Right. Okay, and so how are we going to approach this problem? Well, we're going to use separation of variables again, but if you begin to try to use separation of variables as we did in the last example, you're ultimately going to encounter some issues, in particular because it's harder to understand how to take advantage of this particular boundary condition, right? Well, the key point here that lets us get somewhere is to remember that there are all sorts of rotational symmetries for the Laplace equation, but this is a disk, right? So this is a rotationally symmetric domain. And so we're going to be able to take advantage of the fact that the Laplacian is invariant under rotations and that the domain is also rotationally invariant in order to get to a solution. And in particular, the ideal will be to try to solve it using separation of variables, but with polar coordinates instead of x and y coordinates, right? So let me write this out. Right, so this is the key idea. Right. The first point is that, well, the domain dA is rotationally invariant, meaning if I rotate the disk about the domain about the origin, it doesn't change the domain, right? Right, if we rotate about the origin, the domain stays the same. Right, well, this is not true for rectangles, for example, because like, remember, maybe the rectangular domain could, if you rotate it, it'll look more like a diamond or something like that. Right? Well, we also know that the Laplacian is invariant with respect to rotations in the sense that we talked about in detail in the last lecture, and also has a nice formula in terms of polar coordinates, right? Right, and so the idea will be, well, we have all these rotational symmetries on this domain for both the differential operator and also the geometry of the domain. And if you remember from multivariable calculus, whenever you had like some kind of rotationally symmetric domain or a domain that involves circles or spheres or disks, it's often very useful to use polar coordinates because polar coordinates will make a lot of your calculations simpler. And so both of these points together tell us, well, let's use polar coordinates to solve it. Right. And so this is what we're going to do. And so let me just set up the problem. Right. So note that we can describe the domain D in polar coordinates as well. Well, it's the set of points r comma theta with, well, r is between 0 and a, less than or equal or bigger than or equal to 0 and strictly less than a. And theta is between 0 and 2 pi. Right. And also we can describe the boundary of our domain is the set of r theta with r equals a and 0 less than or equal to theta less than or equal to 2 pi. Right. Right, and we're just using the standard polar coordinates, right? R is the length of this line, right? So if I pick a point inside the domain, right? So the length of this will be r, and then theta is the angle, right? So in this case, theta would be this angle here, right? Relative to the x-axis, right? Well, if I vary theta between 0 and 2 pi, I pass through a full circle, right? And then if I vary the length r, this depends on the radius of the circle, and so the circles can go from the origin out to, it can stop right before it hits A, right? So anything. Right, sorry, there's a bit of a bug there with the recording. Okay. Right, and so finally, well, right, so we're gonna view U as a function in polar coordinates, right? Well, remember that we have the following representation of the Laplacian in terms of polar coordinates. The Laplacian of U is given by second derivative with respect to r plus 1 over r times the first derivative with respect to r plus 1 over r squared times second derivative with respect to theta of U as a function of r and theta. And so we're going to view the Laplacian as this differential operator in these coordinates. And then we're going to use separation of variables for U as a function of r and theta, right? So we're going to guess u of r theta is given by some function f of r times some function g of theta, and then apply the separation of variables method. One thing to point out is, well, how do we understand the boundary condition? Well, the boundary condition u, right? Well, at the boundary in polar coordinates, r is just equal to a, right? So the only thing that's varying is theta. So this is a function of theta, right? Between 0 and 2 pi. Right, so for example, let's say this is the y-axis, and this here is the x-axis. Well, when theta is equal to 0, you start off over here, right? And as you increase theta, h could have different values along the circle. But right over here, when we come back to theta equals 2 pi, well, these are describing the same point, right? And so, well, we better require, unless there's some kind of inconsistency, we need to require h to have the same value at one point, right? H is a function, it can't take the same two different values at the same point. And so therefore we want to require that h of 0 is equal to h of 2 pi, right? So this is a periodic condition, right? So we're going to require, right, u of a theta equals h of theta. This is our boundary condition, where h is periodic in the sense that h of 0 equals h of 2 pi, and more generally, h of theta is equal to h of theta plus 2 pi, right? So let's assume this full periodicity condition. And so using this perspective, we'll be able to solve the problem. And in fact, we'll get a much simpler, it's still going to be a little bit complicated compared to maybe what you're used to from other earlier classes, but we're going to get a much simpler formula than we did for the rectangle, which was kind of nasty. Okay, that's it for today.